Hi everyone, I'm Eivinas. This is joint work with Josh, Ying, and Niko Kriegeskorte, and the title is Attention Enables Flexible Energy Efficient Vision. So cognitive scientists have long hypothesized that the function of visual attention is to allocate limited energetic resources. And in this project we asked, but how may this actually work? And our answer is a model. EN stands for Energy Efficient Attention Network, and which provides a mechanistic account of how attention controls visual hierarchy via learned top-down multiplicative gain signals, and how these sorts of mechanisms may improve the energy efficiency of vision. So to test our model, we implemented this novel visual category search task. On each human behavioral trial, participants see this search image for 100 to 400 milliseconds. There's always one and only one target digit. Here is a 4 and a bunch of distractor letters. Then we flash a mask just with distractor letters to terminate recurrent processing and a flash iconic memory. And inspired by David Marr, who said that to see is to know what is where by looking, we asked participants to click where they saw the digit, which class it belonged to, and also rate the difficulty of that particular search trial. And in this talk, I'm going to ignore human behavioral data and just going to focus on the modeling. But we use the same task for the model to evaluate the model. So how does the model work? So energy efficient attention network, on each time step, it receives an input image, in our case, the search image, process it using a visual hierarchy, which is implemented as a convolutional neural network, followed by what we call an attentional controller, which is implemented as a recurrent neural network. The recurrent neural network keeps a hidden state across time, so it can integrate its information across time. Importantly, the attentional controller computes this top-down modulation, top-down attention signal, which is implemented as multiplicative gain that can modulate the processing in the visual hierarchy. And on each time step, the model predicts the what and where in our task. So for this particular time step in this image, the model thinks that there's a 1 at this upper right corner of the visual field. Unlike some of the traditional deep neural networks, EN minimizes not only task errors, but also energy use. So our loss consists of a task error component for both what and where, as well as this energy use component. And here we consider both synaptic transmission and action potentials. And this lambda energy is an important parameter that controls the cost of energy. So by setting different values in the loss for lambda energy, we can have different trade-offs between task errors and energy use. How do we compute energy use? So consider this really simple one-layer neural network. Synaptic transmission, you can think of it as like the activity along each synapse. So if you take each weight and multiply it by the input, take the absolute value and sum across all the weights, you get what we call synaptic transmission in our model. And for action potentials, we simply sum the outgoing activations, the y's. And importantly, we measure energy use for all components of EN. So we implement a similar calculation for the convolutional layers in the visual hierarchy, for all the recurrent layers in the recurrent neural network, and all the other smaller components of the model. And we consider a bunch of different attention mechanisms. So the baseline model has no attention. EN Global implements what maybe classical cognitive scientists would call a temporal attention or arousal, where the attentional controller predicts one value that upregulates or downregulates the visual hierarchy on each time step. EN Feature predicts these like feature gain vectors that modulate the convolutional layers along the channel dimension. EN Spatial modulates spatial locations. And then EN Full is the most complex that combines both feature and spatial gain. So within the same architecture, we can implement like these classical notions in cognitive science of attention, like temporal attention, feature-based attention, and spatial attention. So here's how the one inference trial for the full model. So we enroll the model for 4 time steps, and we present the same search image to the model on each time step. Here, the target digit is a 7 in the upper right corner. And we can visualize first the feature gain and spatial gain. And particularly the spatial gain is quite interpretable, where on the first time step, the model is unsure what it's looking at. So the attention is quite uniform, but then at the end, it focuses on the target digit and inhibiting the distractors. We can also similarly visualize the mean activation across channels or across space. So if you look at, again, similarly with like space, like in the beginning, units across the visual field are active, but at the end, only units that have the receptive fields over the target digit are active. And you can get an intuitive sense of why this sort of spatial attention would be helpful to minimize energy, because in our model, activations relate to energy use, and the model can focus the activations on very particular parts of the scene that are relevant. And then we can also visualize the predictions in both what and where components of the task. So on the first time step, the model is unsure what it's looking at, predicts roughly uniform distribution, but then at the end, it converges that it's a 7 in the upper right corner. One main modeling result is that attention actually improves energy efficiency. So on the x-axis, we have the mean energy used per trial for action potentials and synaptic transmission. On the y-axis, we have the what accuracy, like the classification accuracy of the digit. And here's the baseline model. So all of these little diamonds are different model instances trained with different lambda energy, the energy cost parameter. So if it's really small, then you get models that use a lot of energy. If it's really high, then you get models that use less energy, but are potentially less accurate. And similarly, we can plot all of these different models. So as we increase the complexity of the attention mechanism, we get better and better energy accuracy trade-offs. And a similar story can be told about the where accuracy. So the full model dominates all other models in terms of the energy accuracy trade-offs. So the big story is that attention improves energy efficiency, and there's also this interesting gradient where like increasing the complexity of the attention mechanism gives you better and better gains. Ian also explains human behavior. Ian captures some classical neural effects of attention, but there's no time for that. So to conclude, energy efficient attention network is a mechanistic account of how attention controls visual hierarchy via learned top-down multiplicative gain signals. It's an account of how attention may improve energy efficiency of vision. And it seems that cognitive science assumptions about attention are vindicated. With that, I would like to thank Niko and Josh and my lab, the ZIFest organizers, and you for listening.